So today we're looking at quantum machine learning. For the past 2 weeks, or let's say in the previous weeks, we've been looking at classical machine learning using LSTM. So we're picking the merchandise trade flow information from the Bank of Ghana, and we're running it in a classical LSTM model to make predictions into the future. So today we'll take a look at what quantum machine learning is all about before we do some short practice on that. So what is machine learning? Machine learning basically is a field that integrates quantum physics concepts with, that is for quantum machine learning. Yeah, so obviously you have to see that there have to be a quantum aspect to the machine learning. So it's just integrating quantum concepts with machine learning techniques, and that is what gives birth to quantum machine learning. So the quantum computer is a whole new class of computing system that increases the hardware available for machine learning through quantum machine learning. So machine learning is a very, very important field in the field of computing, where we try to make classifications based on data we receive, or we make some regression activities or tasks, or we make some predictions into the future, or to forecast something into the future to see what is likely to happen, so that we can put measures in place to resolve that even before it occurs. So quantum theory, which is based on completely different physics, is the foundation for information processing using quantum computers. So very, very important that we explore this field of quantum machine learning. So as you can see from this image, we have in the middle the quantum machine learning. So it means it draws some aspects of quantum computing. It draws some aspects of machine learning. It draws some aspects of optimization techniques. It draws some aspects of intelligent algorithms, draws some aspects of big data, draws some aspects of quantum information processing. So there's various elements that come into play when we are talking about quantum machine learning. So we know that every element usually demonstrates some form of particle or wave properties. If you have studied quantum physics or quantum mechanics, you realize that every particle has a wave and a particle property. So, for example, a particle such as electron, photon, or any other quantum entity exists in every possible state in accordance with the laws of the quantum realm. So, and this existence in the various possible states is what is known as superposition. So for entities or particles within the quantum realm, they can exist in a superpositional state, as they can exist in a multiple state at the same time until they are measured. So one demonstration of this superposition principle is the Schrodinger's cat experiment, where it's like you place a cat in a box, and that box contains a flask full of poison. Now, we place some devices or some components that will break the flask and release that gaseous poison in the box. So as the box is sealed, we cannot really tell whether the cat is still alive or is dead. So at that point in time, we can say that the cat or the state of the cat is in a superposition state, because we can't tell whether it's alive or dead until we open the box to really see what has transpired with the cat. Then we can tell for sure whether the cat is alive or dead. So that is a superposition state that we are referring to. So this superposition state is actually a probabilistic state, and that we have to take a look at. So it is crucial because without the ability for quantum objects to exist in two states simultaneously, the computers you will use will not be able to function. So that's very, very key. What are the building blocks of quantum computing? We know that zeros and ones are the bits that are used in classical computing. For quantum computing, we make use of qubits, and they are still basically zeros and ones, only that this time around they are surrounded with the Ket notation. So, and that is what differentiates it from just being an ordinary bit or being qubit. So for classical physics governs humans, and we eventually live in a world represented by classical physical science for anything that is larger than a molecule. So you agree with me that anything larger than a molecule, we are actually talking more of a classical realm. But anything that is a molecule or smaller than a molecule, we are actually diving into the quantum realm. So um, we have to understand that one very fundamental principle of entities or particles in the quantum realm, one has to do with quantum entanglement. So for quantum entanglement, if you want to look at it in the form of particles, so we can say that it is the interconnection between particles such that one state of one particle can affect the state of another particle. So that is what happens. There's a correlation between the particles. So if I have qubits, I can have qubits that are also correlated together, and that correlation can be made possible by means of quantum entanglement. So that must be understood. So we have large companies like Google, IBM, and NASA who are already devoting time and resource into the development of quantum computing. Machine learning. So machine learning is all about complicated mathematical calculations with large dimensions of data. So means machine learning, actually you have to use some data, and machine learning cannot really exist if there's no data, because what will you be, what are you predicting? What are you classifying? You need data in order to be able to perform all of these tasks. So um, since a qubit can contain both 0 and 1, we can say that n qubit is 2 raised to the power n bits. So if I have 1 qubit, which gives me 2 bits, I can have 2 qubits that gives me 4 bits. I can have 3 qubits that gives me 8 bits, and so on. So let's imagine I have 300 qubits. That is almost 2 raised to the power 300, and that is a huge number of bits we are talking about. So the ability of quantum computers, especially when it comes to qubits, is very, very high. So one major problem that we have had is that, for example, if I have a quantum computer and I have a classical computer and I have some data, let's say that data, the size is 300 qubits, and I'm trying to bring it in a classical computer, which obviously you should know that you require a huge amount of space in order to deal with that qubits that is being transported in the classical computer. So because of the conversion from qubits to bits is very, very high. So a lot of computing power, a lot of computing resources will be required. So that is a major challenge in the world today. And if you can come up with a novel solution to actually find a way to convert qubits to bits without a large amount of storage space and all of that, then you might make a very big breakthrough. So you can explore that and see. Some of you might have novel ideas as to how to deal with that. So machine learning with quantum computing, usually there are libraries that you use in machine learning. One of them has to do with TensorFlow Quantum Library, uh, which provides primitives for developing models here and there. So that is something that most machine learning experts usually use, TensorFlow, TensorFlow. I'm sure most of you have heard of TensorFlow. Yeah. So why quantum machine learning? Well, no, machine learning has proven to be super useful in everyday life. So machine learning today uses different processes. So those of you who have classical computers and you are running machine learning models and algorithms, obviously you are dealing with the CPU, the central processing units. But some of you might be having the GPUs, which is the graphical processing units that you are using to run your models. Some of you might have TPUs, and usually that is for large organizations and stuff. So we also have what is known as the QPUs, the quantum processing units, which could be used as special purpose machine learning accelerators. So that is very, very important and must be understood. So quantum computing could also lead to new machine learning models. For example, we can have quantum kernel methods, we can have quantum neural networks, we can have convolutional neural networks, we can have the quantum Boltzmann machines, the quantum generative adversarial networks, and so on and so forth. So what are some of the QML approaches? So we have CC, CQ, QC, and then QQ. So what is CC? CC basically means classical to classical. So we can have that is usually talking about entirely classical methods that are used for machine learning. So in this particular one, there is no quantum computation involved. So we are looking at purely classical methods. That's the CC. For CQ, we are looking at classical quantum. So classical systems can use quantum resources for specific tasks. Yeah. So we can talk about an example like solving sub problems or performing computations. So for QC, you're looking at quantum to classical, and that one has to do with um, that is the use of classical resources to augment various operations. So you realize that for the QC and the CQ, there's a classical component, there's a quantum component. So it depends on what you are looking at. If you are using classical resources to augment quantum operations, then we are looking at quantum classical. But then if you are using quantum resources for specific tasks, but then we are using a classical system to do that, then we are looking at we are looking at CQ. So we also have fully quantum, that is a QQ. So quantum to quantum. So this we are looking at fully quantum approaches where both data processing and learning components are implemented quantum mechanically. So it's very, very important and must be understood. So what are some key concepts of QML? We have variational quantum circuits. The main QML method has to do with noisy intermediate quantum devices. A noisy intermediate scale quantum is also known as NISQ. NISQ. I'm sure most of you have heard about NISQ. So NISQ is basically refers to the current generation of quantum computers, which are characterized by their intermediate number of qubits, and they are susceptible to noise and decoherence. And then, as you are aware, this noise and decoherence is what has become a major problem of quantum computer and a major limitation. So realize that there's a lot of work ongoing when it comes to the elimination of noise, quantum error correction, noise elimination, and all of that. So that has to be understood. So What are some general steps for quantum machine learning? Basically, you just prepare some fixed initial state, then you encode the classical data into a quantum state. And in order to do that, you might require some layers to do that. Then we now process that quantum, that data that we converted from classical to quantum state. We now process it using a processing layer, or better still, a parameterized model. Then we perform measurements in order to see the outputs or to extract observables. So this is an example of a variational quantum circuit. And you can see that this circuit actually is made up of the R, Y, R, Z, and RS gates. And you can see that we have two parameterized layers here. And some measurements is being taken at the end in order to get an observable or get an outcome. So in quantum machine learning, obviously, there's also training in there. Just like classical machine learning, you train the model with data. You also do same with quantum machine learning. And it's very, very important we understand that. So, but principally, it looks like the neural network fields for quantum machine learning has been explored a lot. So you find that a lot of works, a lot of people actually talk about neural networks, especially when talking about quantum machine learning. So we also have what is known as some hybrid computation, where we can have a classical aspect and a quantum aspect. So we can have what is known as a hybrid quantum machine learning approach, where you can have some aspect of the model being classical, another aspect being quantum. So it depends on how you interplay the classical and the quantum within the model, and that will make it some form of a hybrid approach. But obviously, the quantum machine learning we do now can say is basically not fully quantum, because even we are still using our various computers to run these quantum machine learning models. And these computers are classical in nature. So you realize we are not actually dealing with a fully quantum system or a fully quantum machine learning, because at some point in time, a classical machine learning is even used to run the algorithm. If we wanted to go fully quantum, then we need to run this algorithm actually on a quantum computer or quantum hardware. Yeah. So we can have a hybrid neural network such as this. So we have the classical component of the neural network, and we can have a quantum node in between here, and then we can have some output that is given. So this is a merge of classical node and a quantum node, and that forms some form of a hybrid neural network. So we can have that also in place. So what are some applications of quantum machine learning? Um, I've mentioned extensively of what some of the neural networks and the machine learning algorithms can be used for. One field that is used a lot is the pharmaceutical industry. Now, in drug development, pharmaceuticals, medical equipment, they also make use of quantum machine learning. If you want to develop drugs, now sometimes it takes a very long time to develop drugs. For example, just imagine some years back, or just some few years back, we had this COVID-19 pandemic, and it took a very long time to even come out with a vaccine. And you know, some of these viruses and things are they are very, very tiny. They are actually quantum in nature. So what would have been the best computer to analyze such a virus? The quantum computer would have been the best computer to analyze, because since the virus is quantum in nature, using a quantum computer will ultimately make our work very fast. So it will make processing of information very quickly so that we can actually get some vaccine. But then you realize that the quantum computers are still at a very young stage. So we are still relying on the classical computers, and the classical computers too will take quite a long time. So actually, when quantum computers fully develop, and then you realize that it will be very, very good for the pharmaceutical industries and the health sector and all. So some application of quantum computing imposed with machine learning. So we can have some of them here, as I said, drug design. So when it comes to the drug design and stuff, it's very, very important we use machine learning in order to speed up activities or tasks. So quantum machine learning could also probably help to mitigate errors here and there. So we have something more like an enhanced quantum computing. We can also have various things that quantum machine learning can actually be used for. So whether simulation, whether enhanced quantum computing, whether even performing some data analysis, or whether um, doing some sensing or forecasting of weather, you realize that quantum machine learning can be very, very useful in these areas. All right, so for quantum data analysis, we can use quantum machine learning. For quantum chemistry, especially drug development and material science, can benefit greatly from quantum machine learning. And also in the optimization of tasks and activities, machine learning can also be used there. For anomaly detection, especially now that we're dealing with a world full of anomalies, cybersecurity issues and stuff, quantum machine learning can also be very, very crucial and important there. Obviously, and quantum cryptography as well. But then we have to understand that even though quantum machine learning is a very exciting field, it has its limitations because quantum hardware is still limited in nature now. And even one of the limitations, as I said, has to do with the noise and decoherence issues. And so they're trying to develop quantum computers with very, very less noise because other than that, if the noise is so much, then the quantum computer become very, very unusable. So the task for today, we are going to look at the data processing of the merchandise trade flow dataset. We'll look at how we can define the quantum device, define the quantum cell function, define a custom Keras layer that wraps the quantum LSTM cell. We are going to build the Keras model with the quantum LSTM. I'm going to process each time step with the quantum LSTM time step layer. We'll concatenate these time steps outputs along the time dimension. Then we'll perform layer normalization for compatibility in graph mode. We also have to define the dropout and the dense layer, and especially the dense layer for the final output. And then we define and compile the model and then train the model. So that's the task for today. I'm following the same pattern as we did for the classical machine learning using the merchandise trade flow dataset. So most of the things we did for the classical model will remain the same. We are not going to change anything, but the only part we are going to work on is the model aspect. And that is where we introduce the quantum model in there. That's a quantum enhanced model. But basically, the data pre-processing that we did will all remain the same. So let's jump onto some coding. Right, so I hope I'm still audible.
Yes.
So for this,
Yes, please, we can hear you.
All right, so we are going to do some pip install TensorFlow 2.1, PennyLane 0.26, AutoRay 06, 0.6.0. You need to install these libraries first. Very, very important. Then we import these various libraries like we did. Import NumPy, Pandas, import PennyLane, TensorFlow, Matplotlib, import. This is not very important. OpenAI, that one we can leave that out. You can import TensorFlow. I think this has been repeated, so let's take this off. Yeah, this is not also very important, so let's take that one to off. All right. So we import all of these libraries, and then we set TensorFlow global policy to float 64. So we want all the data that we process here to be in float 64. You know, we have float 32 as well. So, but I want it to be in float 64 because of the model that we are going to be using. It requires that you have your data in float 64. So we define a file path as we have been doing, the merchandise trade flow.csv. We read from the file path, and then we display the data. In fact, let me just run this so that we can see what is happening at any point in time. I hope this is mounted. Let me see. Okay, so let me run all. So some installation is actually ongoing now, so it will take some time. So that is the installation of the TensorFlow, PennyLane, and AutoRay. So let's wait for that to finish, then we import our libraries. Okay. Restart session. All right. Okay. So we've installed our libraries, and then we've imported the various libraries that we need. And then we read the merchandise trade flow data into the data object. This time around, you can decide to print out to see what is in there. You can decide to go ahead if you are very sure that the data is intact. So let's just display what is in there. So let me just run from here. Let's see. All right. So we have our data, the trade merchandise trade flow data. So we are sure that our data is really inside the data object. All right. Here, remember what we did over here? We tried to verify to make sure that our data that we are loading into the model has these various columns. If it doesn't have these various columns, then we know that our data has a problem. So we make sure that all of these columns exist in our data. Then we define a function to replace zeros with the mean of the non-zero elements in the row. I think I've talked about this already. Our data contained zeros for some of the months. So in order to streamline that, we had to compute the average of values that were there, so that we use that average to fill for the rest that is containing the value 0. So I think those of you who are there during the classical machine learning would have understood this. They went ahead to shuffle the data indexes and then split the data into a training set and test set. Then we created some training and test data sets so that we can feed it into our LSTM model. Because LSTM model, you have to create the data set in a particular way. So the function to do that is this. We place the training set and the data set here so that you can create some training and test data sets that will be conducive for feeding into the LSTM model with a time step of 12, because we are looking at 12 months. Then we created a data pivot in order to so that variables becomes columns and each row corresponds to a year. So to restructure the data in the CSV file, we created some data pivot to do that. And I'm sure most of you understood up to this point. So as I said, the pre-processing activities that we did for classical machine learning using the merchandise trade flow data, everything is basically the same. Everything is the same. The data pre-processing that we did, everything is going to be the same. The only difference is that where we are supposed to define the model, that is where we have to make some modification and changes here and there. So if we understand that the pre-processing stage, everything is the same, let's just jump straight to the main aspect, which has to do with the definition of the quantum model and all, so that we can move from there. So let me create a cell for that. Let me just run all of this again. Okay, nice. So so as I said in a PowerPoint presentation, I said first we're going to define the quantum device. I listed a number of steps that we're going to do. So we're going to follow that particular procedure to actually create our model. So first of all, we need to define the quantum device. So let's define the quantum device. What I mean by quantum device, we are also specifying the number of qubits, because for the merchandise trade flow information, we're predicting 11 variables. In that case, we need to set our n qubits to 11, and then we create our device using the n qubits. So this is how to define the quantum device. So after setting the n qubit variable to 11, we say dev equals qml.device, the bracket default qubit, ys equals n qubit. We have defined the quantum device. Then after that, you define the quantum cell function. The quantum cell function. So at qml dot q node dev. Now dev interface equals tf a diff method equals parameter shift Yeah. So we create our function def quantum, let me call it LSTM cell. Then we have our inputs. These are set two parameters, inputs and weights. Inputs and weights. Then set our inputs. Set our inputs. So let's cast the inputs and weights to. Don't remember I said every data must be in float 64. So let's cast it to 64. Then the same for the weights. We cast that as well. Okay. After casting or after typecasting the inputs and weights to float 64, we create a pad, or we pad the inputs to match the number of qubits. We pad the inputs to match the number of qubits. So padded inputs is equal to
Yeah, hello, Doc.
yeah.
Please, I want to ask, is where you define you connect the device to the node,
Is that?
where you connected the device to the node, the Q node,
Yeah.
and inside that brackets, that interface TF and those diff method. I don't really get this one.
Yeah. So I'll explain them later. I'll
Okay.
explain them. Yeah. So you just follow on. You write down your questions, then I'll answer them when I'm done.
Okay.
Yeah. So padded inputs equals TF dot pad inputs. Yeah. So minus TF dot shape. TF dot shape inputs. Okay. So yeah, we are padding the inputs to match the number of qubits. That's what we are basically trying to do. Expected index or slice expression. Okay. Yeah. So we now perform some data encoding. using this. So for I, the range of n qubits, which is 11, QML.ri, so we are basically encoding using the RY gate. Then we define some strongly entangled layers for LSTM, like processing. So we say QML dot templates dot strongly entangled layers. So weights ys equals range and qubits. Take this out. Then we measure each qubit poly z expectation value. Yeah, so we have defined the quantum cell function. The next thing is to define the custom Keras layer. That is going to wrap the quantum LSTM cell. So class quantum LSTM time step layer. So def init. So the super quantum LSTM time layer, but init then self dot n qubits equals n qubits. And self dot q widths equals self dot add width We define the shape equals weight equals weight underscore shapes. Initializer equals random underscore normal. The D type the data type equals float 64. Printable equals true. Name equals keywords. We define another function def call, which accepts two parameters self and inputs. Define a quantum computation within the Keras layer. So we say output is equal to quantum LSTM cell input self. So we have the weights and the inputs being passed to the quantum LSTM cell function, which in turn is assigned to your object output. So we can return TF the shape TF the cast okay. Now let's build the Keras model with quantum LSTM. So we'll say input layer equals TF dot Keras dot layers of input the shape equals 12, 11. Remember, we are talking about 12 months and 11 variables. So that's why the shape is 12, 11. And the name equals input and the D type float 64. Better still, you can say TF dot float 64. That should also work. So the weight shapes equals We process each time step with a quantum LSTM time step layer. The time step outputs so define a loop for I in range of 12. That's to do with the 12 months. The time step equals tf.keras dot layers dot lambda and we say time step layer equals quantum LSTM time step layer, and you pass the n qubits and the weight shifts. Then define your time step output equals time step layer, then time step outputs dot append time step output. Yeah. Then we concatenate the time step outputs along the time dimension. So we have quantum LSTM output equals tf.keras.layers dot concatenate function with an axis of 1, data type D type equals tf.float64 . So we are concatenating the time steps output. That's the output of this that's along the time dimension. Then we perform layer normalization for compatibility in graph mode. So it's a layer norm output equals tf.keras dot layers layer normalization Yeah, specify the D type to be TF dot float 64. We now define our dropout layer as well as our dense layers, our dense layer. So dropout layer, the dropout layer, say dropout equals tf dot keras dropout say 0.3 name equals dropout name equals dropout. Now define our dense layer. The dense out equals tf dot keras the layers dot dense then specify the kernel regularizer to 0.001. Then the name equals output. And the D type equals tf.flow64. And attach the dropout. We concatenate the dropout layer. So, in effect, you define the model. And in defining the model, you say model equals tf.keras dot models dot models dot model input equals input layer and the output equals the output equals output. So after defining the layer, we can define the custom loss function. Let's define a custom loss function and a custom root mean squared error function because we are looking at the regression activity. And for regression tasks, you can be performing precision recall, F1 score, and so on and so forth. You have to do what you can determine the loss, you can determine the mean absolute error, you can determine the root mean squared error, you can also determine the mean squared error. So that is what we are going to do. So let's define our custom loss function. So we can say um, Def custom loss y true and y spread. Y true, y spread. So y true equals TF dot cast y true. Then the data type TF dot flow 64. Then we have y spread. So we are just doing some typecasting over here to 64. So we do that as well. Then we define a variable and we say y true minus y spread. Then we say the loss equals TF dot reduce mean TF dot square x. So this is the custom loss function. Then you return the loss. Then we define a custom root mean squared error function. So custom root mean squared error function. So we say def root mean squared error. So y true, comma, y spread, then return TF dot SQRT return TF dot SQRT TF dot reduce mean bracket TF dot square so y spread minus y true now let's compile the model. The optimizer equals TF dot Keras dot optimizer dot Adam. We are applying a learning rate of 0.001. Then we say model dot compile, and the model dot compile we supply that with the optimizer. We'll say optimizer equals optimizer loss equals custom loss. Then we can define the various metrics. The various metrics. We have the mean squared error. Then we have the root mean squared error. The root mean squared error. Then we have the mean absolute error. The mean absolute error. For the root mean squared error, because we have defined a function here, then we need to remove this so that it uses this defined function that we have specified. Other than that, it would have picked, if there's an inbuilt root mean squared error function, just pick that and use that. Now let's ensure all inputs, the input data is explicitly in float 64. So we say X string scale equals the np.array X string scaled d type equals np.float 64. Well, let's just copy and paste to make work easy. So X train scaled, then we look at Y train scaled, then we'll look at X test scaled, then we'll look at Y test scaled. So let's do okay. So we've converted our training and test scale data now, which we are going to feed to the model in order to train the model. So let's go on to that. So how do we train the model? We train the model, and I'm sure most of you know how to train model. We just model.train, well, model.fit, sorry. Then we're going to pass some, we'll say X train scaled, the X train scaled, Y train scaled, epochs. Because this is a quantum model, if you set your epochs to 100, it will take a very long time for the data to finish training because of the limitation. We are using a classical computer to access a quantum resource, which is on the cloud. And that might take a very long time. If you're running this on an actual quantum hardware, it would have been faster. So, advice we Let's just set this to 5 epochs for now to avoid any delays. Now batch size 32. Okay, validation data. Let's put that immediately after here. Then batch size was 32. Let's have some callbacks, especially the early stopping mechanism. So you can say callbacks equals this tf.keras.callbacks.early stopping, where we monitor the value loss with a patience value of 10. So best width equals true verbose of 1. So at the end, we can print a message, quantum enhanced LSTM model trained successfully. So let's just manage. In fact, let's set this epoch to 1 and just run and see so that we don't waste so much time. Let me rerun everything. Hope that there's no error in here. There's no error. This was never closed. Okay. tf.shape is that it's never closed. Oh, okay. Def root mean squared. Okay. What is the issue here? No colon. All right. Let's run all. Okay, define the model. Name output is not defined. Where is that? Model equals this. Model equals name output is not defined. Model equals tf.keras.models.model. Inputs equals input underscore layer outputs equals output. Oh, okay. That's supposed to be an output object here. Output equals df.keras the layers dot reshape 12 11 dense output. Okay. Run everything again. Optimizer equals tf.keras.optimizer.adam. What is wrong with that too? tf.keras dot optimizes. Okay. Mm. Wow. So our model has run successfully. That's nice. Let's set it to 5 epochs and rerun. So if you run this on your local computer, it will be much slower than running it on Google Lab, because Google Lab actually have supercomputers and stuff they use. So you realize that running the same model on your computer will be much slower compared to running it on Colab. So that is what we have. Since it is fast, then let me just set that to 50 epochs and see. I hope it doesn't slow down our system. All right, so that is how we can run a quantum enhanced model, a quantum model, still using the merchandise trade flow information. So we have a loss value of 0.0445, mean squared error 0.7462, root mean squared 0.8638, mean absolute error 0.6978, and so on and so forth. So you realize that here we defined a quantum device. We then defined a quantum LSTM, quantum cell function. Then we defined the quantum LSTM time step layer. And then we built the Keras model with a quantum LSTM. Then we process each time step with quantum LSTM step layer. Then concatenate the time steps up along the time dimension. Perform a layer normalization for compatibility in graph mode. We specify the dropout layer, the dense layer, define the model, and then define custom loss function, some custom functions, root mean squared error function. We compile the model. We ensure that all input data is explicitly in flow 64. Then we train the model. So you can see that the performing quantum machine learning is not all that difficult. The only thing is that usually some aspects of it is classical, because the data pre-processing and all that we're doing was basically on a classical computer. Then we just fed that data to a quantum model. And this quantum model actually, we trained it and we came out with some inputs. Now, after that, you can go ahead and perform your predictions and stuff as we did for the classical computing. Remember, we even went ahead to perform some predictions where we could predict values for month 1, month 2, month 3, all the way to month 12. So you can follow the same pattern for the quantum model as well. And that will give us some predicted values. So that is what you have to understand. So quantum computing basically, quantum machine learning basically uses the same machine learning techniques that we know in classical computing. But then this time around, it has some quantum properties that are also defined, like entanglement, superposition in place. And that is what brings about the difference. So it is hoped that quantum machine learning will actually be better than the classical machine learning that we have now, especially when it comes to the pharmaceutical industries and various industries that requires the prediction of information like weather forecasting, disaster forecasting, and all that. Imagine that the objects can be in a superpositional state, and objects can be entangled such that one state affects the other. Then you know that we are actually looking at a computing technology that is very, very strong and powerful. For entanglement, you are all aware what it is. So one object correlating with another object. And that is very, very important, especially if you are talking about quantum teleportation, not the transfer of uh, entities, the physical entities, but then teleportation, you don't need to really transfer the physical entity. The state of that entity can be transferred, and that can also be teleportation. So I'm sure most of you have probably come across um, teleportation or quantum teleportation. So um, that is very, very important and must be understood in that light. All right. So I think this is what time will have me do. So if there are some questions, then you can ask them and I'll see how best to address them. I think somebody asked a question on
I was asking on the
you said the NQP is plus 11, then the QML the device default dot what?
yeah, the device when you give it to the node and you were saying interface is equal to TF and then the parameter shift.
Yeah, so basically just trying to define the quantum cell function. You know, with LSTM, especially with quantum LSTM, you have to define a cell function that uses some interface. And that interface is what's known as TF, that is TensorFlow.
I also guess it was TensorFlow, but I was not just trying. I was not correcting. I was not sure whether TensorFlow or something like.
Yeah. So basically, you know, we are using various libraries in specifying all of this. So the TF is TensorFlow. Then the parameter shift, a diff underscore method equals parameter shift. Basically, has to do with that's actually a method that uses the parameter shift rule to compute gradients. So if you want to compute various gradients, then we need the parameter shift passed to the diff underscore method. So we are basically specifying the differentiation method used to compute gradients of the quantum circuits parameters. Basically, that's what we are trying to do.
Yeah. Okay. Thank you very much.
But you know that the TensorFlow tool, you can interface it with Qiskit or SEC or PennyLane or any of these quantum machine learning libraries. You're aware of that?
Yeah. I knew it's an interface for even the neural networks as well.
Oh, okay. Are there any other questions? The way everyone is silent, I'm sure maybe this was not very easy compared to the classical one we did.
But please, Doc,
Sir, like my question is about the code. Are we going to have it or we
Yeah,
should
yeah.
work?
You mean the notebook? I can send the notebook to you. This
Okay.
particular notebook, I'll send it to you so you can access it on your platform. You guys are on a platform, so you
Yes.
access the notebook and then you manipulate it here and there to do whatever you want it to do.
Okay, thank you.
Yeah. Well, if there's no other questions, I think you can take it up from there. Do your manipulation analysis. Just there is not anything difficult. You can easily understand it. The pre-processing stuff is the same. The only thing is that the definition of the model and the devices aspect is different, a little different from that of the classical approach that we looked at. So this is just the quantum equivalent of the classical approach that we did last 2 and last 3 weeks. Yeah. So if there are no questions, maybe I'll bring my presentation to an end here.
thank you very much.
Yeah, you're welcome.